right, we're very happy to have Peter van Hintum give a number of quantitative or quantitative ability, I think it was, right, of geometric inequalities.
Yes, thank you. Yeah, thank you for coming. I want to talk about a collection of geometric inequalities and their stability. And let's start with maybe the most famous one, which is the isoperimetric inequality. It's goes back to ancient times. What does it say? It tells you something about the relationship between the surface area and the volume of a set. In particular, it says that if I have some set in Rn, I'm going to be a little bit vague about the sets and functions I'm going to be talking about because I don't want to get too technical. But the basic concept is that if I have some set in Rn, the perimeter or the size of the boundary of that set is going to be at least that of the ball of the same volume. So this is a ball that has the same volume as it. And maybe let's be a little bit precise by what I mean by this perimeter here, because of course there's different ways of defining that, but the definition that I'm going to use the following is going to be the perimeter of A is going to be the limit as time goes to 0 okay, still maybe a little bit vague. Let me quickly also define what I mean by A plus B for two sets in some group. This is just going to be the set of all sums of two elements when A and B. So why is this the perimeter? Quickly, set A. I get this ball. Sorry, I should specify. This is a ball of radius epsilon. If I add a ball of radius epsilon to a set A, I'm going to get a set that is ever so slightly bigger than A. So this distance is going to be epsilon everywhere. And if I then remove A from it and I divide by the width of this little shell around it, I'm going to get a measure of the size of the boundary.
Does the limit always exist?
Sorry?
Does the limit always exist?
So, okay, I want to talk about sets A that are somewhat reasonable. So pick your notion of reasonable that you like, and then it exists. Yes. All right. So, but with this definition in mind, what does this inequality say, or what does this inequality ask? It's essentially saying I want to minimize this quantity. And what sets A would minimize this quantity? Well, one example would be the ball of the same size of A. Okay. But in this picture, the only thing that changes as I vary A, of course, the volume of A stays the same. So the only thing that varies is this sum, A plus B epsilon. And it's saying this sum A plus B epsilon is minimized if A is a ball. Okay. Let's derive, or let's generalize that a little bit. There's a thing called the Brunn-Minkowski inequality. What does the Brunn-Minkowski inequality say? It says that if I have A and B in Rn, now there's many ways of formulating it, but let me start this way and say that if I want to think about the size of their sum sets, what shape should, or what set should A and B be so that the sum is minimized? It's essentially saying, it's actually still the ball. So it's still true that if I take two sets and I replace them by the ball of the same volume, that is exactly the object that minimizes the system, or an object that minimizes the system. And if you then compute what is the size of the sum of two balls of a given volume, you're going to find that it gives a lower bound of this form. The idea being to determine the radius of the ball that you get, you take the volume to the power 1 over n, and that is then given by the sum of the radii of the other two. Okay. In this case, the minimizer was only the ball. I didn't say that yet, but in this case, actually, the family is a little bit richer than just the ball.
Are A and B convex?
Sorry?
Are A and B convex?
No, not necessarily. Not necessarily. No. Yeah, so again, for instance, this to be measurable, there are some, you need to be a little bit careful about what A and B you pick. But take reasonably behaved A and B. So I like to think of them as finite unions of convex sets, for instance, where there's no bound on the number of convex sets that you get. Okay, and in this case, we get equality if and only if A and B are homothetic convex sets. Up to a measure 0 sets. Again, all my R should be interpreted as for all reasonable sets to little errors that I don't want to get into. So morally, whenever I take two homothetic sets, their scale is determined by the 1 over n of the volume, and those scales add up in the exact same way they would in a ball. Okay. Now, I could talk for hours about Brunn-Minkowski inequality and its stability. And I have done that exactly here. I've talked 4 hours on the stability of the Brunn-Minkowski inequality in the computer science discrete math seminar. So, I mean, I see a lot of overlap with the people who were there, but if you're interested in that, I would refer you to the recordings of those seminars. And rather, I would like to go one step further and move beyond sets in Rn and rather talk about functions. And let's see, what can we find something similar for functions? Now, maybe actually let me start by taking a little sidestep and reformulating slightly the Brunn-Minkowski inequality by saying, okay, I still have these sets in Rn, but now I'm going to assume that they have the same volume. And I'm going to take some parameter between 0 and 1, which is going to measure the fact that secretly they don't have the same volume. So that I'm going to take the weighted average between the two sets. Maybe I should specify what I mean by this weighted average. It just means that I'm going to take this sum, but now I'm first going to scale the sets. So what do I mean by scaling the set? I just multiply all the elements in the set by the scalar derivative. Okay, so visually, what does this weighted average between x and y mean? It just means take a point in x, take a point in y, and take the weighted average between these points. Okay. Now, why do I prefer this formulation? Because I don't have to bother with the ends anymore. And all it says is that if I take the average between two sets of the same volume, then it actually, that weighted average always has at least the volume of the two individual sets. So slightly cleaner, and also the equality becomes a little bit cleaner. So I get equality if and only if x is y. I now drop the homothety because they are now already the same size. So x and y are pretty essentially the same. They might be translated, they might vary in a measure zero set, but they're essentially the same. And that set that they both are is a convex. Okay. Now I translated it to this world because this is going to be slightly more amenable to the functional context. So what is my setup going to be? I'm going to have these functions f and g, let's say from Rn to Rn greater than 0. And akin to this world there, I'm going to assume that they have the same integral, which is parallel notion of the volume. And now I need a notion of taking the average between two functions. And akin to what I meant by taking the average between two sets, there's many ways of defining this, of course. But let me throw one family of ways of doing this on the board, and then hopefully I can convince you that this is a somewhat natural way of taking the average between these two functions. And again, as before, I'm going to take the weighted average. And I'm going to introduce one more parameter p, which we'll see in a second. This is, let's take it in R. I'm going to define the following as the mean between these two. Let me draw. So before, to take the average between a set A and a set B, I took a point in A and I took a point in B, and I took their weighted average, and I said, oh, this weighted average somewhere between them lies in the average. And I want to do something similar for the functions, okay? So let's say I have some function defined here, some function defined G, some function F defined here, some function G defined here. I'm going to think, what is my average going to be on this point in the middle? It's going to be some weighted average of the functional values at the extreme. Okay. So let me write one way of doing that down. I'm going to take the supremum. So let's say I want to evaluate this at a point Z. I'm going to take the supremum over all x and y, which average to this point Z. Z. And I'm going to take the supremum over all weighted averages between f and these 2 points. And in particular, I'm going to say, I'm going to take the p average. So I'm going to say, let's take lambda times fx to the p, 1 minus lambda g of y to the p to our 1 over. I'm going to take some p mean between these two values. I'm going to take the supremum over all of them. And it's the same way sort of that I did here. To determine whether a point was in my set or not, I was going to see if there even existed a pair that would put this point in. Now, a few interesting things happen. One thing is what happens at p is equal to 0. What happens at p equal to 0? It's a bit weird, right? This definition doesn't really make sense. So let's think what happens as p tends to 0. What happens with this average? Where does it go? Sorry?
You get a log.
You don't quite get one. So let's say I fix lambda, I fix fx, I fix gy, and I just let p tend to 0. where does this average go?
Geometric mean.
Geometric mean, yes, very good, very good. So I'm going to give myself a little bit more space. So first the case, if P is not 0, it's going to be this object. If P is 0, it's going to be again the supremum, but now over the geometric mean between these two. All right.
It is a log.
Sorry?
It's the average with respect to the lambda is a log of f plus log of g.
Exactly.
Yeah.
Exactly. Yes. Right, very good. Scary definition. Somewhat daunting, but let's see if we can work with it. If we can see why it makes sense. I want to put one more caveat, which is that no. Let me focus on the P is 0 case first, and then let's see where we go.
Voor mij I have to. If you take characteristic function, when do you recover the characteristic function?
Exactly. Yeah, so that's exactly where I wanted to start, which is, let's say that f and g are characteristic functions. So let's say for a second that I consider the average, let's say the weighted, let's say p lambda or lambda p? Lambda p. Lambda 0 of the indicator function A and the indicator function of B. What is this function going to be? Well, it's going to be exactly non-zero if both of these are 1. And where does that happen? That happens exactly if they're weighted average, if they're the weighted average between a point in A and a point in B. So this is going to be the indicator function of lambda A. Now, skeptical people among you may have noticed that if I didn't pick 0 there, but I picked another P, things go a little bit, some slightly strange things happen for indicator functions. So I want to add a little clause here, which is that I don't want one of the two to be 0. One of the two values to be 0. So this average that I'm going to take is always going to be 0 if one of the two functions is 0. So let me add that as a little clause. We're lucky that in the 0 case that actually doesn't matter, because then it would immediately appear. But for P is not 0, it does.
That's a slightly disturbing clause to add.
Sorry?
Disturbing thing to add, right? Because now it's very sensitive if G is very small or exactly 0.
True. Yes, yes. And it might make us a bit happy about P is 0, like prefer P of 0 over other P's. Yes. So with this clause in place, this actually holds for whatever P. Now, I've attended some other colloquia and some other seminars this term for the special year. It seems like the people who are here for the special year really love log-concave functions. So I thought maybe that's a nice perspective to motivate this object. Because what is a log-concave function? What do we know a log-concave function to be? We say a function L, let's say from Rn to greater than 0, is log-concave if for all x and y in Rn, and lambda between 0 and 1, I find that L of the weighted average of 2 points is at least the geometric mean of those 2 points. Okay, which in terms of this object here, we can easily rewrite as L is equal to m lambda 0, L and L for all lambda between 0. Okay, so hopefully this sort of makes sense. Yeah, maybe we can push a little bit more on this notion for the log concave function and how it relates to this. For instance, by maybe the following example. Sorry.
Why is L equal M lambda 0? Yes, no? Greater or equal?
Well, you mean it's greater than equal? Yeah, that's true, but it's always all the other implication is immediate, right? Because at any point, I can always take the average between L and itself.
Okay.
Yeah, yeah. Yeah, exactly. Maybe let's do one more example, which is, let's say I take my log concave function L over R2. R2. Okay. Now I want to evaluate the following function capital L from R greater than 0, which is defined by integrating along a line. So this is going to be the integral of L xy over 1 axis. Okay. And now, in order to evaluate this object, let me consider some line x and some, so this tends to infinity on both sides, and some line x prime. And let me consider the function L on those lines, and specifically a line in between, some weighted average between. And notice that, let's say this is x plus prime. Notice that for every point on this line, I find that by the definition of what it means to be log concave, for every pair of points on these 2 other lines, which go through the point that I'm interested in, I get a lower bound on the value of L at that point. Okay, so if I think of the function L on this line, it's lower bounded by this weighted average between the function L on the 2 extreme lines. Right. So how does that relate to this integral function? I now realize that I haven't written the inequality yet. But my claim is going to be that this capital L is itself a log concave function. And the reason for that is the big inequality that I mentioned at the start, the Prékopa-Leindler inequality. So what does the Prékopa-Leindler inequality say? Well, it's been hinted at already of what it might say. It's saying that if I take this this weighted average between functions f and g with the same integral, this weighted average has at least the size of the integrals. So let's say f and g is there. So let me recall that f has the same integral as g, and I take some lambda between 0 and 1, then the integral of m lambda 0 of f and g is at least the integral. So with that in mind, we find that we found a lower bound on the size of the integral of L along this line. Right. Okay. Let's see some more applications of this Prékopa-Leindler inequality to get a bit more of a feel for it. Maybe some that are a little bit more. A little bit more. Sorry?
Will you always suppose from now on to be 0?
No. No, that's a good question, but I don't want to give away yet what the book Borell-Brascamp-Lieb inequality says. So we'll see that in a second. So let me first give a quick proof of why Prékopa-Leindler inequality follows from the Brunn-Minkowski inequality. Just to get a bit of a sense of why I call these things geometric inequalities. Because of course we're talking about functions now, but in my heart, we're still talking about geometry. It's just number of dimensions has slightly grown. Okay. So let's say the proof that Brunn-Minkowski implies Prékopa-Leindler. All right. So we're given functions f and g, as in the statement of the Prékopa-Leindler inequality, from Rn to non-negative numbers. And I'm going to want to use the Brunn-Minkowski inequality. So I want to construct sets. So we just saw that the Prékopa-Leindler implies Brunn-Minkowski by turning sets into functions, and now I want to do the reverse to show that Prékopa-Leindler follows from Brunn-Minkowski by turning these functions into sets. And I'm going to do it in the following way. I'm going to define the set xf in Rn plus n as follows. I'm going to take all the points in Rn and at a given point, I'm going to put a little cube in the m remaining dimensions.
What was M?
M
Yeah.
is some integer.
Oh, you didn't tell us yet.
I'm going to put a little cube, an m-dimensional cube of volume fx. And I'm going to do that for all the points in R. Okay, and same thing for G. So now let's see what we know about these xf and xg. Well, let's start by the simple note that if I want to evaluate the volume of xf, it's just the integral over all of these cubes. So it's just going to be the integral of f. Okay, and the same is that's the same as g is the same as x of g. Okay, so what does Brunn-Minkowski tell us about this set? Well, it tells us that the weighted average between these sets has at least the size of the individuals. This is at least. Okay. But what is this weighted average?
Some exponents.
Sorry? Sorry, I'm now using this version where the sets have the same volume. Yeah. Okay, so let's explore what is this set. And to explore that, I'm going to consider what happens at some point in Rn. Well, I'm going to take, it's going to be the union of a bunch of sums of cubes or averages of cubes. So I'm going to take here the union over pairs x and y with the property that their weighted average is z. And in those points, I'm going to get the weighted average of the cubes in xf and xg. So this is x up to the 1 over m plus 1 minus lambda. Right, all right. And this might look a bit scary in terms of that this is a big union, but of course all of these are nested because they're all just cubes. So really, this object is just determined by whatever thing maximizes this this value there. So really, in terms of what we were talking about before, I can rewrite this. This is the same. Lambda 1 over m f and g of z m okay. We'll see where this is going because the volume of this object is just the integral of m lambda 1 over m of f and g. Okay, and now with a little bit of care, we can take so there's a bit of a hand wavy step. As I take m to go to 0, this actually tends to this 0 average. Sorry, yeah. This is as
Yeah, you don't seem to have enforced this condition that f of x times g of y is positive. Is that right? In your definition of big M, you add an additional. That's not the same. That's not true here.
Yes, you're right. I should have defined this slightly differently. Apologies. This should be an open interval. An open cube. Yeah. It's quite important, of course, that if f of x is 0, you don't get any points in these places. Yeah, apologies. Yeah, all of these. Yeah, so in this place, again, we have the addition that both of those are not. Very good. And so this proves a Prékopa-Leindler using Brunn-Minkowski in increasingly high dimensions, which motivates the perspective that Prékopa-Leindler is just sort of an infinite dimensional version of Brunn-Minkowski, given some symmetries in the sets that you're working with.
Is this definition of m lambda p, is it kind of motivated by this argument, or is there some separate reason you would define the mean that way? For p not 0.
I guess it is motivated. Yeah, I'm not sure if it's motivated by this proof per se, but more by Brunn-Minkowski inequality itself. Right? I now realize that I should also put a clause here that A and B are not empty. yeah, you need to really rule out the most degenerate cases. All right, so maybe a relatively natural natural relationship between these two inequalities. And maybe also that gives a sense of maybe this is where the story should end, right? The best notion of average that you can take should be 0, and this is just the inequality that corresponds to it. No, okay. So what was the realization of Brascamp-Lieb and independently Borell a few years after this Prékopa-Leindler proof was published, that actually you can push it a little bit further. I mean, not by the proof that I've shown you, but actually if we consider these averages, we can actually go a tiny bit further, namely for P at least -1 over n. I still get that M3 of F and G is at least true. Does it seem to follow us all from our proof? But I think the main motivation, this is sort of the intuitive way why this might be true, is that in a way you get the reverse of the Brunn-Minkowski. So it's essentially saying that in the direction of the function, you lose a bit, but that amount is exactly compensated by the fact that in space you gain a little bit. So a way of seeing that is that if you take f and g to be multiples of indicator functions, you can see this to be true. Yeah, there's a different proof, just maybe the more combinatorial proof of Brunn-Minkowski, which is based on induction, where you maybe, I don't know if people have seen this before, you assume the sets to be union of axis-aligned boxes, and you cut with parallel hyperplanes. And you continue to cut until you're left with the sum of 2 axis-aligned boxes. And then you prove the Brunn-Minkowski inequality for those boxes, and then by induction, the Brunn-Minkowski inequality follows in general. And a similar argument does also give Prékopa-Leindler and does also give this Borell-Brascamp-Lieb. Oh, so much time has passed. Okay, I was going to talk about stability. So now that we've established what the inequalities are, let's maybe first see what the extremal objects are. Fortunately, those are relatively easy to describe. So we saw that we had convexity in the case for sets, and we saw also in a way the natural extension of the notion of convexity to functions if p was equal to 0. There was this notion of lock concavity. So here we have equality if f is essentially g, and they're both lock concave. And for the Borell-Brascamp-Lieb inequality, things get a little bit more tricky. So I'm not going to give the equality cases in full generality, but I'm going to take the case where p is bounded away from -1 over n. So equality if p is strictly bigger than -1 over n, if and only if, again, if f is essentially g, and they're what I will call p concave. Now, I just gave a definition of what it means to be lock concave. It was that a function, when averaged with itself, gave the same function back. And that is what I'm going to use also to define P concave. So I'm going to say a function is P concave if the should be a different lambda than that one. Let's say gamma P of F and F is equal to F for all gamma between zeros. So it's saying that as I take this weighted average, my function just is. The details here for Borell-Brascamp-Lieb are not the most important, but I thought it was good to point out that you can actually push a bit beyond zero. But let's focus on zero for a second. Forget about these details. And let's think about stability.
For bodies could translate one as since nothing is it the same here?
Sorry, Dan.
Bodies you could just translate one and nothing change.
Yes,
Is it-
yeah. So it's exactly, it's here, it's true as well that as you shift the yeah, that's not an issue. Yeah, so those concerns I'm trying to hide in the is essentially equal to up to translation. And again, up to measure zero differences. All right, so let's talk a little bit about stability. So what do we mean by stability? We have these inequalities and we have these descriptions, hand-wavy descriptions of when equality is achieved. And we want to find some stability. So in the notion of, okay, we might not have actual equality, we almost have equality. Does it mean that the objects that we're considering are also very close to the extremal objects that we have described? And maybe let me start all the way back for the isoperimetric inequality. So we saw that we had the inequality that the boundary of a set A was at least the boundary of a set of a ball with the same volume as the set. Landmark result by Simonyi, Matilli, 2009, it was shown that if the set A is at most 1 plus delta times this minimal boundary, then it must look, the set A must look a lot like a ball in the following sense, that the symmetric difference between A and the ball is at most the square root delta times the size of A times some constant depending on
Or suitable to
for up to some, yes. Two. Yeah. Okay, and this kicked off a big study in this direction. Let me know.
Sorry, is the interesting part of the statement that there's a polynomial, the dependence in delta, is it meant to be sharp?
Yeah, so I was gonna, so this is optimal power of delta.
And what's the set that?
It's you take a ellipse by just slightly perturbing a ball. Yeah. So I think the optimality is a little bit easier to see in the next statement. So that's where I was was going with this. Maybe let me put it in the middle. So a lot of work was put into getting, and successfully so, put into getting stability results for the Brunn-Minkowski inequality. For the sake of time, let me just restrict myself to one of the endpoints of that study, which said that if I have A, B, M, and as before with the same volume, and some parameter T. If the weighted average between A and B is at most 1 plus delta times the size of the individual sets. In this case, I'm going to put an extra condition, namely that delta is small in terms of the dimension and the parameter T that measures the average between the two. Then they must be convex in the following sense, that there exists a convex K, so that up to translation, we have that A and B are subsets of K. And this containment is actually quite tight. K minus A plus A minus B is at most the same notion as before. This grows with the square root of delta. For this example, it's relatively easy to evaluate because it can be studied just by considering two rectangles which vary by a little root delta perturbation. If you compute the weighted average, you'll see that it shows that root delta dependence is actually shown.
You know, I think I asked you this in the talk, but just to remind us, the isoperimetric inequality follows from the Brunn-Minkowski inequality, but that statement does not follow from the statement, right? Because you have to take T go to the.
Yeah, correct.
So these are two completely different worlds. We should think of those as being separate.
Yeah, so actually, since you asked me that question, I had some more thoughts about it, and in some special cases, it does actually follow.
What is special?
A and B convex. Actually, as a result of the talk you gave about mixed volumes, I think realized they could be applied to get some relationship. Yeah, but you're right. It doesn't follow immediately. Yes. And now we actually realize that you can get a slightly different result, which wasn't really available in that world, which is that these two sets A and B themselves are actually very convex. So we find that they're similar to the same convex set. But if you just are interested in how convex the individual sets are, you can get an even stronger result, namely a linear result. Yeah.
Go wait, that's the convex hull.
Sorry.
Yeah, sorry. Yeah. I should say. So this is the convex hull of A. So the smallest convex set that contains A. Very good. And of course, the same holds for B, just by symmetry. So I spoke at quite some length in the different seminar about the ideas behind the proof of this, but let's see what we can say about the Prékopa-Leindler inequality. and see if we can get stability. And the answer is yes, unsurprisingly. And now, before I give the statement, let me point out that the Prékopa-Leindler inequality, the stability thereof, doesn't immediately follow from the Brunn-Minkowski inequality, exactly because of all these dependencies on the dimension that I mentioned here. So the proof that I gave of Prékopa-Leindler just used Brunn-Minkowski, but of course the dimension I take goes to infinity, which means that if I wanted to apply any of this, all the constants would completely blow up and there's no hope of really giving anything. And in a way, that is morally correct, because some of these results in the strength that I stated them here are simply not true for Prékopa-Leindler and for functions. Namely, let's say I have some function, this is just a one-dimensional function, that is just, let's say, the indicator function of some reasonable interval in the middle, but then also has a little peak far away. If I wanted to take the smallest, if I want to do something like this, where I take a log concave function that contains my function, i.e. it's an upper bound to my function everywhere, then as this point flies off to infinity, this log concave function is going to absolutely blow up. But actually this mean between this function and itself is not going to blow up, because I can make this very small. And making this very small is something I cannot do in the world of Brunn-Minkowski, because I'm working with indicator functions, so I can't just make a point small. The point is always 1. So this idea that I get these sets that actually contain, these functions, these log concave functions that actually contain my functions, there's no hope for that. So to quantify how close I am to such a function, I'm going to need a slightly different measure. And that's the following. So again, FG, 0, same integral. I have some, let's forget about the p, let's just focus on p is equal to 0. I do have some lambda between 0 and 1. And if I find that my weighted average is at most 1 plus delta size, with again, delta should be small in n and lambda, just like it was above. Sorry, no, in this case, I don't actually need it for some silly reason. In this case, there exists a log concave function L, which is close to f and g in symmetric difference systems. So if I integrate difference between L and F and L and G, then this is at most square root delta away from the functions F and G. All right, and we get the same result for Borell-Brascamp-Lieb, where you need to replace log concave with p concave. We get the same result. And again, this dependence is optimal exactly for the same example. Like you could even take genuinely just indicator functions of these rectangles again, and we show that this dependence is optimal. Hmm, 5 minutes left. Maybe let me use that to mention one thing about the fruit, which also connects to one of the difficulties, namely in this world of Brunn-Minkowski, the convex set K that I should choose is maybe not super hard to determine, because I just take my two sets A and B and I overlap them so that they nicely overlap, and I take the convex whole of their union. And I just overlap them in such a way that the convex union, the convex whole of these two is smallest. In this world, finding the appropriate log concave L that is close to F and G is a way harder task, right? Because I can't just take the log concave whole of one of the two or overlap them. Like it's a lot more tricky. And as it turns out, we use a version of the second part of the theorem here to yield what L to choose. So we don't find literally this result, a linear result, but we do find a linear result in the case that F and G are the same. So we do show that if m lambda 0 of F with itself is at most 1 plus delta times the integral of F, then there exists a log concave L, so that the symmetric difference between F and L is at most linear in delta. And here the basic idea is for this theorem, that means how is applying this L for given an F. Again, we can't take the smallest log concave function that is larger than F. That one might be too big. But the basic idea is quite a cute one, I think, which is I'm going to take the minimum log concave L so that the following quantity is the following inequality is true, that if I let F prime be the minimum of F and L, so I cap F by this function L, then the amount that I remove from the mean is big compared to the amount I remove from F. The amount that the mean goes down is relatively a lot compared to the amount that F shrinks, and so C is some small constant depending on L and sorry, lambda and F.
Don't understand what is the mean by min log, minimum log?
Yeah, so okay, again, I'm being a little bit vague here. So I'm going to pick, let's say, a minimal log concave. I'm going to pick an L as small as I can. So the property that there's no other log concave function, which is upper bounded by this original log concave function. So the smallest in that sense, which has the property that this inequality holds.
But you fix C first.
Yeah, you fix C first. C is just a constant depending on lambda. Yeah. And now the L that you pick is just a minimal one for which this is positive. And this has the nice property. So if we go to the example that I saw before, where you just had an indicator function and then a little point here. If we think about the mean between this function and itself, is going to, of course, have the function itself. And it's going to have some little blob somewhere in between the indicator function and the point. So if I take my L to just be, let's say, this function here, what do I remove from this mean? It's going to be this whole block. That whole block is now going to be gone. But what do I remove from F? It's only going to be this tiny little blob. So as long as I can remove bits from F, which remove relatively a lot from the mean, that is very interesting. Okay, and I'm afraid that I'm out of time. So
Are there any more questions?
So what kind of independence do you get on the error there, the ON?
yeah, so in this one, trying to think what the limiting factor is. So all our arguments have reasonable dependencies on n. I mean, far from optimal. Even our dependence on lambda is not optimal, which is somehow even more frustrating. So I'm not quite sure, but nothing too crazy. Maybe that's yeah.
And can one tell what happens when lambda tending to 0 or the constant thing?
Yeah, so we don't have the sharp dependence as lambda tends to 0.
But outside of 0, nothing happens.
Sorry.
If you decide to be something away from 0 and 1, then it's uniform.
Yeah. So there's some dependence in this constant, in this implied constant.
But only when you go to the extremity of the interval.
I mean, if it's a half, it's just a constant. Yeah. I mean, the result really holds for all lambda between 0 and 1. I guess only in the case if our functions f and g to start with were log concave, then you do get the sharp dependence on lambda. So that's a nice one. But that's actually for, in a way, a quite silly reason. It's just, in a way, just a consequence of the Prékopa-Leindler inequality. That says that if your result, if you have a bound on this mean for some lambda, and f and g are log concave, then you actually automatically get a bound on the same average, but with lambda replaced by a half. Yeah, and in fact, we realized the other day that we also get it in the same way for free if the smaller of the two, so if let's say lambda goes to 0, and the case that in the case that g is log concave, so sort of in the limit as you put less and less weight on the non-log concave function and more weight on the log concave function, which is sort of the opposite limit as the isoperimetric limit, in which case you put less and less weight on the non-convex set. So it's a little bit strange, but it's just a little quirk of the Prékopa-Leindler.
And you were already supposed an integral from f and g, but is it just for convenience and you can?
Yeah. So all the results also hold if f and g don't have the same integral. The only thing is that the statement is a bit. So for instance, the Prékopa-Leindler inequality, if you remove this assumption, you get some weighted average of the two integrals. Yeah, you just get this m0 lambda again. So here it's not too bad. But in the Borell-Brascamp-Lieb statement, You also get a weighted average of F and G, but there, the weighted average that you get is, it's a bit ugly to write down, I think. So it's a lot cleaner if you work in the case where F and G have the same engine. Yeah, but all the results, I mean, it's really just one line extension. There's nothing going on. Yeah. Sorry, I saw your question
I
before.
wanted to answer the same question, so.
Okay.
Okay, if there aren't any more questions, let's thank Peter again for the great talk.